Hello friends, so we are back here with another video that is regarding the drinking water. This is not a drinking water, this is a packaged drinking water. Since those are sold in the market, as you can see nowadays, different companies sell it in different volumes. That is from 500 ml to 1 liter to 2 liters to 5 liters up to 10, 20 liters. The question is this packaging, the packaged drinking waters, the quality of this packaged drinking water is a question, and another question is that this 20-liter package, regarding this 20-liter package, this 20-liter package, these packages are not thrown away. They are not once used, they are not disposable, they are used number of times, plenty of times. These lower volume packages are not used number of times, they are just once used, and their end is there. That is the end. That is the end. That is the end. So, but this 20-liter package, there is no end. This is continuously taken away by the vendor, and it is again supplied by the vendor. Sometimes the bottles are changed, but the same bottle to someone's bottle comes to somebody, somebody's bottle goes to somebody. So this goes on. So we are going to discuss about this in this video, about this 20-liter package. Mainly we are concerned about this 20-liter package, and we are discussing this package regarding this 20-liter package. They are stored for a long time in their godowns, not sometimes these godowns are garages. Even they are not proper godowns. The water storable godowns, these food quality storable godowns are not there. This even in the garages they are stored, and there is also question. And many days they are kept for many days, for about 15 days, 10 days, 1 month, 2 months, 3 months, even 4 months they are kept. So therefore, two aspects rises. One aspect is the chemical property of this water, and the second aspect is the microbiological property of this water. Whenever any medium is kept for long time, prolonged time in any storage, there continuously it goes through a temperature difference, a weather difference, a climatic difference. So climatic change rather, temperature change, weather change, climatic change, this goes on. So these affect mainly on this liquid medium very fast and very effectively, and especially this water, it affects very fast and very abruptly it makes an effect. Those which are not seen clearly by our naked eye. So therefore we have taken around 100 ml of this sample to make experiment to see the quality of this water. The two aspects we are going to check, what just I have said previously. One is the chemical aspect, and another is the microbiological aspect. Now, what is this chemical aspect? Microbiological aspect, we all know that we will see this water under microscope, and we will be examining like our previous videos. We will be examining for parasites, these microorganisms, these funguses, the bacteria, and all that. So that's a plain story. That is a known story to us already. But what is this chemical aspect? Now, this chemical aspect there is a very dangerous thing. This is a very story is very dangerous behind it. So let's discuss very wisely. So the thing is that when this package is kept, this water is kept in a plastic package, it is very for a long time, very periodically, it is not changed. It is kept for a long time, for 1 month, 2 months, 3 months, in a place, such a place where the temperature varies from top to bottom, from low to high, so where the climate changes from hot to cold, cold to hot, and winter season goes away, so in between. So this type of variable places where the climatic condition changes is variable. So what happens? There are the two molecular aspects. One is the water molecule, and other is the plastic molecule. Now this is very important. These plastic molecules are organic molecules, and water is a polar molecule. It is half organic. So what happens? There is a molecular exchange takes place from the organic plastic layer to the polar water layer. The polar water layer also contains hydrogen atoms. The plastic also contains CH, the hydrogen atoms. They also contains these hydrogen atoms. They also contains the polar atoms. They also contains the oxygen atoms. So this type of polar exchange, this type of molecular exchange takes place between this water and the plastic. Sometimes I don't know whether you have examined or not, carefully examined or not. If you have smelled an empty medicine bottle, especially a vitamin bottle, whether you have examined or not, I don't know, but you will find when there is a empty medicine bottle, bottle is empty, which consists some medicines, salt, and especially the vitamin medicines, the vitamin B complex and vitamins medicines. They are content used to supplied in bottles. So have you questioned yourself that when you open the empty vitamin bottles and the smell of vitamin comes inside, there is no vitamins, there is no medicine inside, but the smell of the medicine is coming out. Why? Why it is that? There is no medicine, there is no tablets, there is no capsules, but and the bottle is empty, but some medicine smell is coming out. Why this happening? Actually, this is happening because of the molecular exchange of the vitamin and the bottle content or bottle plastic bottles. Therefore, it is not mandatory, it is a mandatory rule that which is not followed as usual, that this type of food elements and these medical elements, medicinal elements, are not to be sold or not to be stored or not to be kept in plastic bottles, PET bottles. These are polyethylene and tetrahalline bottles or PET bottles or polyethylene bottles. They are not supposed to be supplied, but unfortunately they are supplied. So therefore I am actually raising a video regarding this packaged drinking water. So be careful about this packaged drinking waters. So therefore, we are going to study this packaged drinking waters. We are going to study the two aspects. One, the microbiological aspect, another one, the chemical aspect. This chemical aspect is much more dangerous than this microbiological aspect, because microbiological problem or the microbiological system, you can alter by boiling, just boiling the water, or just by porous filtering the water. Is a very vigorous filtering. If you go through, if you put this water, if it contains any microorganism, if it contains, suppose we think that it is containing a microorganism, maybe salmonella, but maybe flagella, maybe cryptosporidium, which I showed you in my previous videos. If they are present, if some gram-positive bacteria is also present. But nowadays, a very improved filters are available. Ceramic filters are available. Very good ceramic filters are available. So these filters, if we purchase from a reputed place, and if we use it, and if we pour this water to it, and we can filter it out and keep in any clean glass bottles, we store it in clean glass bottles and glass jars. Therefore, there will be no microbiological problem. The microbiological problem will be solved. But what about the chemical problem? If there is a molecular exchange between the plastic molecules and the water molecules, if the plastic molecules gets attached with the water molecules, if a CH bond has got attached with the polar water molecule, what will happen? Then that is not rectified. That won't be rectified by any mechanical filter or any boiling. It will alter the chemical change, it will alter the chemical composition of the water. So that is more dangerous than this microbiological phenomenon. So we will be talking about these two phenomena. We will be discussing about these two phenomena. One, this water, this chemical property of this water, the chemical situation of this water, rather the chemical situation of this packaged drinking water, and the microbiological situation of this packaged drinking water, which will be proving, which I will try to demonstrate in this video, whether there is any, although there is any molecular exchange of these plastics, which will be, we can get it reviewed from a spectrophotometrical curve. If there is any polypropylene or any organic molecule, there will be a sharp peak rise in any corner, at any wavelength, there will be a sharp peak rise, or any alteration, there will be a sharp peak rise. And then a curve, a semicircular curve, we will see a semicircular curve. Then we will immediately be able to know that there is something extra molecule has come inside this water. So that we will be discussing later on. We will see later on. So first of all, we will see this water. Actually, now at this moment, this water is very clear. It looks very clear. Looks very good. It looks very gorgeous, and is very drinkable now. So what is bad in it? Nothing bad in it. Yes, let's see if it is now. So it looks that it is nothing bad in it. So let us put it in a culture medium and let's see what happens. We will going to put it in a culture medium, and then we will see what bad is there. After 5 days, we will see what bad is there, and we will be testing the molecular phenomenon, the chemical molecular aspect of this, molecular chemical aspect of this, molecular chemical aspect of this water. What is happening? What is there is any molecular exchange or not? That we will see. So let us begin the experiment and see. Hope what comes out. Let's see. So friends, we are ready to begin. So here is our water sample, as you can see, and we will be taking the 6 ml of around 6 ml of this water sample to this flask, and we will be using the dry Glasky selective agar. This is around 3 ml. So this goes around another 3 ml. So 6 ml we are taking. So we are going to put this dry Glasky selective agar to start the culture. So it is done. So it is done. So now we will be corking it and putting it in the incubator for 5 minutes. So here is our cork. So that is corked, and it is will be keeping for 5 days. For 5 days for under incubation for 5 days in 37 degrees centigrade temperature. So friends, the UV spectrum study has been done. So the file is opening, and as you can see, this spectrum, and you can see there is a negative side evolution of the curve. So this is because the polar water molecule has captured the polyethylene. So friends, you have seen from the spectrophotometer curve that there is a molecular exchange. A certain molecular exchange has been there. So but it has been there in the reverse side. That is, there is a bulge, two bulges are there in the reverse side, in the underside of the curve, the graph or the spectrum, whatever you say. So why this is under the reverse in the reverse side? This is because of the polarity of the water. As I have earlier said, that water is a polar molecule and it has two poles. So water is the composition of two hydrogen atoms and one oxygen atom. So if we take the model of this water in front of the picture, this is the model of the water, as you can see. This is the model of the water, and if I hold in the left hand, so this is the two positive hydrogen atoms and this is the negative oxygen atom. Now this is when kept in the polyethylene jar, PET jars. So the plastic molecule comes in intervenes with this water molecule.
Why this plastic molecule will intervene? They will intervene because they go through a very rigorous abrasion. This rigorous abrasion, lots of abrasion is going on over there. They are clean, they are brushed, they are roughed, they are scorched, they are goes through a lot of, and this in between this rigorous temperament, the plastic molecule loosens this, but the whole pet molecule, which is very wide, just now I will show you, it loosens up. And therefore what happens, when, as you can see, this is the plastic molecule, this is the polymer molecule, polyethylene molecule is a very big molecule. You can see my left hand is the benzene ring, and in the right hand the total other part of the polyethylene molecule. This is strong, but the weakest part is this hydroxyl group, this oxygen and this hydrogen group. This is the hydrogen atom. So this part is very weak. So what happens? This goes off. So this goes off, and this is finally loosens up. This is by abrasion, this goes off, and now remains the negative oxygen atom. Now this remains the negative oxygen atom. Here is the negative oxygen atom. So this attracts the positive hydrogen atom of the water, like this. So there is a hydrogen oxygen bond. This is a weak hydrogen oxygen bond, but there is a hydrogen oxygen bond. This sometimes snips off, sometimes conjugates, sometimes snips off, sometimes conjugate, but there is a weak hydrogen atom bond, hydrogen bonding. So this hydrogen bonding, due to this hydrogen bonding, the water molecule, it is a whole PET molecule in my left hand, is carried out with the water molecule. So here is a negative positive attraction. So this negative oxygen atom of this PET molecule attracts the positive hydrogen, one of this positive hydrogen atom, or sometimes both the hydrogen molecule atoms is attracted, and this becomes a very strong bond because this is a double bond. So this becomes a very strong bond with this oxygen atom, and this takes place, happens inside the PET bottle, and this whole plastic molecule with this water molecule remains inside the PET bottle, and this is the dangerous part of this molecular chemistry of this PET water. That is a different kind of water. That makes it, this water is not our drinking water. This is a different kind of water, and this water is a PET water. So this takes place. This keeps on moving inside the PET bottle. So this is the dangerous part of this water. So it is now, it will be clear for to you that this happens. This is the molecular chemistry of this PET water. So other part is now going to we will be discussing later on. That is the microbiological part, which we will discuss later on, because that water is under microbiological incubation. This is in the culture media, as I have shown in the previous video, that is in incubation, and this we will be discussed later on. So
So friends, we are back after 4 days, not 5 days. We are back after 4 days because, like you can see, when the culture media, the drinking water, so-called drinking water, as we were talking about previously. So here you can see this drinking water as the color has changed. The color from the green, as you have seen from the previous video, the beginning of the culture, as I have shown you, that color was green. The dry galactic agar, the color was green. Now the color has become yellowish, almost yellow. So because the pH has changed from from higher range to lower range, rather from the neutral to lower range. So as you can see, presume very easily there is a microbiological change. So the change is what change? This change can be indicated, or rather it can be said from this this culture media view, this just a naked eye view of this pH change. We can say that acid fast bacteria has accumulated, because the acid, or rather acid producing bacteria, or rather the acid, they need acid, so they have made the medium size, that the acid fast bacteria, so they have accumulated in the medium. And maybe some funguses are there, lots of debris are there in the bottom of the tube, as you can see. So lots of tube debris are there. So these debris, they are actually gathered, and therefore they are fungus, maybe funguses are there. So that we will be examining in a microscope, under TTCM 400 microscope. So we will be seeing that what happens. Now just we will put 6 ml in the petri dish as usual, and we will see in the TTCM 400 microscope what is there. So after that we will decide whether we will be going to drink this water or we will just throw it away. So that is up to you. You decide. It is nothing to me, nothing up to me. So you decide after this, showing this video, after seeing this video, whether you will drink the water or what will you do. You decide. See, up to you. I am just presenting the video. It is my work to present the video. It is up to you to decide what you do. So let's see, friends, the microscopic examinations. So, friends, but this is much more worse than what I have thought. Actually, this is Coursa dorsally fungus. This is, and you can see the stealth algae also. This fungus is much more dangerous, and it is Drosa corsally fungus. So, Corsa dorsally fungus. So, Aspergillus is also there. So, we can see three type of microorganisms in this video, and the Aspergillus is there. This is very dangerous fungus, much more dangerous than acid fast bacteria. This is accumulated in the drinking water due to this, and this has came out. This is a very timid type of bacteria and very timid type of fungus actually, and they have came out only because of this dorsally, this Diaglasci agar. It's full of Corsa dorsally. This is Corsa dorsally. You can see the full image, the microscopic image in a full magnification and magnified image. These are the small portions of the Corsa dorsally. This fungus is very bad and is very acid producing fungus. This actually produces acid in the stomach. So you can imagine what will happen if it goes inside the stomach. So there it is. You can see.